So energy which binds the two nucleons together is known as binding energy. Okay. So how do we calculate binding energy here? So binding energy is equal to, the formula is binding energy is equal to delta M into C square. It is measured in joules. Okay. Delta M into C square. It's measured in joules. So sometimes we're writing the electron volt also. How? That is 1 electron volt value is equal to how much? 1.602 into 10 to the power of minus 19 joules. This is the value of binding energy. Sometimes we have to write in the other form also. Now, so mass defect appears as energy which binds the nucleons together. Energy which binds the two nucleons together is binding energy. So binding energy per nucleon. Okay. So here next one is what? Binding energy. Binding energy per nucleon. Binding energy per nucleon. So we are writing here B is equal to delta MC square by A, equal to delta MC square divided by capital. So B is equal to delta MC square divided by capital. So that is binding energy per nucleon. So to combine one nucleon, two nucleons, binds the two nucleons together, how much energy is required for one nucleon? That is known as the binding energy. Okay. Next one. After that, we have we have a graph, okay, for binding energy per nucleon, EBN. Okay, here it is in our textbook, it is represented as EBN, EBN. Here it is represented as EB, and here it is EB. Okay, binding energy, and here in our textbook it is written as EBN, EBN, and a binding energy per nucleon. Here also EBN. Okay, binding energy per nucleon. Is that clear now? So we are also writing that EBN is equal to EBN is equal to EB divided by capital A. Okay, EBN equal to EB divided by capital A. That's a binding energy per nucleon. Is that clear? If you separate
Yes,
these nucleons, we have to supply a total energy equal to EB to those particles. Suppose what is binding energy? How much amount of energy is required to separate a nucleus into its nucleons? That is said to be the binding energy. Okay. I'll write again the definition, one more definition here of binding energy. Binding energy is EB. EB. The amount of energy required, to separate a nucleus into its nucleons, to separate a nucleus into nucleons. The amount of energy required to separate the nucleus into nucleons is known as binding energy per nucleon. Okay, so there is one important graph that we have to discuss. Then binding energy per nucleon as the average energy per nucleon needed to separate a nucleus into individual nucleons. I'll write that also. One more definition for binding energy per nucleon. Okay, is this clear, all of you? Yes. Now, next one is binding energy per nucleon. That is EBN. So, binding energy per nucleon. So, The average energy required. The average energy required. The average energy required to separate a nucleus. To separate a nucleus into individual nucleons. Nucleus into individual nucleons. That is known as one pair. If you are able to separate, then that is binding energy per nucleon. For the total thing, the total energy. Okay, we can also write the amount of energy or total energy. The total energy required to separate a nucleus into nucleons is known as, that is binding energy. This is per nucleon. So we simply write here EB is equal to what? EBN is equal to EBN equal to EB by A. This is the formula to calculate the binding energy per nucleon. Next, there is a graph. We will discuss the graph. Then we'll discuss about the nuclear forces. Okay, is that clear? Quickly copy this one, then we'll go ahead. Okay, so I'll go with the graph. Did you copy this one, all of you? So binding energy, once again, the total amount of energy required to separate a nucleus into nucleons. That's the entire nucleus. That is binding energy. That is binding energy per nucleon means only one pair, like one neutron and proton. So average energy required to separate a nucleus into individual nucleons. So one pair of proton, neutron, to separate them, how much amount of energy is required? That is said to be binding energy per nucleon. Okay, clear? Is that clear? Now,
Yes, sir.
did you copy this one, all of you?
Yes, sir. Yes, sir.
Okay, chalo. So I'll go over one of the important questions of the graph related question. This is binding energy per nucleon as a function of atomic mass. Binding energy per nucleon versus atomic mass. Okay. So if you are plotting a graph like this, based on this, there can be a question. Based on this one, there can be a question. So here, 1, 2. Okay. Next one is what? So 1, 2, 3, 4, 5, 6, 7. Because I need to explain this one. This graph is very, very important. Okay. Now, here we'll start with 0, 50, then 100, 150, 200, 250. These are the atomic mass. This is mass number or atomic mass. Mass number or atomic mass. The second one is what? Binding energy per nucleon. Binding energy. So we write EBN. Okay. EBN. Binding energy per nucleon, MeV. This is in million electrons. So 0 to 0, 2, 4, 6, 8. 0, 2, 4, 6 EBN versus M. I'll take one more box here. System. So this is the value, okay? EBN versus mass number. So here, the first one is the binding energy per nucleon is practically constant. First, let me draw this graph. Okay, this is for all the elements, how it is. How much amount of energy is required to separate the two nucleons in each and every atom. It's not the same for every nucleus. Like suppose, I want to separate a proton and neutron in lithium, and I want to separate a proton and neutron maybe in calcium. The energy required is not same. It's different because there are attractive forces inside the nucleus, like between the proton and neutron, or proton and proton, or neutron and neutron. There are so many attractive forces, or repulsive, whatever it is. There are so many types of forces. So because of that, the amount of energy required is not the same. It is different. Okay. So, so it will be how much now? Up to here. It will be from here to go to this point. Here. Then go here. Then go here. Okay, it's coming something like this. Okay, it goes something like this. Okay, so I'll write the name of the elements also. This is hydrogen. This one is this is hydrogen, and this one is helium. 1H1, 1H. This is 1H1, 1H2. This is and 1H3. Then we have lithium. Helium here. This is helium. Then this is lithium. Then nitrogen, carbon. This is nitrogen. This is carbon. Oxygen. 16, oxygen 18. This is oxygen. This is oxygen 18. Then we have sulfur. This value is sulfur. And then we have iron. This is Fe, iron. And then we have molybdenum here, MO. Then we have indium, iodine, sorry. Then tungsten, W, then An, then uranium. Uranium 238, something like that. They have given this one. So what did we find out from this particular graph? What are the conclusions? So they did, okay, they see once again, binding energy per nucleon, what exactly is this graph about? See, there are two definitions. One is what? One is binding energy, and the second one is binding energy per nucleon. Binding energy means how much amount of energy is required to separate all the nucleons, total amount of energy, to separate all the nucleons in the nucleus, from the nucleus. That is binding energy. When I speak about binding energy per nucleon, it is only one pair, proton and neutron. How much amount of energy is required? One pair. Now, when we come to each and every element, like suppose lithium, sodium, potassium, there are so many elements. Okay, amount of energy required in hydrogen, we'll not take hydrogen, we will take maybe lithium. Amount of energy required to separate a proton and neutron in lithium is not the same as amount of energy required to separate a proton and neutron in sodium. Got it? Did you understand this? So that amount of energy is not the same, it is different in different elements. So that is why they have to plot as this graph. Why did they do that? Because of this only, they came to know how much energy. So that is how the nuclear energy concept started. Nowadays, we are using fission and fusion and all. How did they come from this graph only? When they came to know how much amount of energy is required, then it is easy for us to select an element. Now, the first one, he says that it is practically constant. The binding energy per nucleon is practically constant. And it is practically independent of the atomic number. From where to where? The first one. The first one, what are the conclusions? The main features of the plot. Main features. We'll discuss about the feature. Then we will go to the nuclear forces, which is very simple. Then we have radioactivity constant. Very, very simple. Okay, it goes faster. This graph is important. Sometimes they will directly give this graph. Sometimes they have asked this graph to draw also. Sometimes they are asking features of the this graph also. Now, the first one is what he says, binding energy per nucleon, EBN. The first point, EBN is practically constant, is constant. From where to where it is constant? From when atomic number between, when the atomic mass is between 30 to 170. It is a straight line, almost a straight line. See, from 30 to 170, it is almost a straight line. 30 to 170 is almost a straight line. So no need to worry. Second one is what? The maximum is 56. When A is equal to 56, number one. When A is equal to 56, the binding energy is how much? Binding energy is 8.75 MeV. Binding energy per nucleon. Binding energy per nucleon is 8.7 MeV. Okay, 8.775 MeV, and 238 7.6. 238 7.6. A is equal to 56. Binding energy is 8.7 MeV, and A is equal to 238. It is 7.6 MeV. That's the first point. The second point is what? EBN is lower for both lighter nuclei and heavy nuclei. Okay, the second conclusion or the second feature. So second feature, he says that EBN is lower for A less than 30. Is lower for A less than 30 and A greater than 170. I think. Yeah. A greater than 170. See, this is also important thing. What is that? It says that EBN is lower for A less than 30 and A greater than 170. Is that clear? Next one. We can draw some conclusions from these two observations. Understood once again? EBN is constant from where? 30 to 170 it is constant. And the second one is it is lower for less than 30 and greater than 170 also it is greater. It is less, very less. The value is less. Means the amount of energy required to separate the proton and neutron whose atomic mass is less than 30 and greater than 170 is less. But whereas for the other one it is like this. Okay, for 36 to 238, this is for 238 is highest, sorry, 7.6, and 56 to 8, very less difference, not much difference. Okay. Now, so we have some conclusions to draw from this one. Please write this faster, then I'll write the conclusions of this particular topic. Is it clear, all of you? Now, there are some conclusions. Okay, conclusions from these two observations. Conclusions of this one. Number one, first conclusion is number one. The first conclusion is the force is attractive and sufficiently strong to produce a binding energy of the force is attractive and sufficiently strong to produce a binding energy of few million electron volts. Is the first conclusion. The second conclusion is the constancy of binding energy here. So the constancy of binding energy, the nuclear force is short ranged. The constancy of binding energy from where 30, that is A less than 30 and 170, tells that it is the force is short ranged. Okay, the nuclear force is short ranged. Okay. Third one. That is very heavy nucleus A is equal to a very heavy nucleus. A is greater than 240. A equal to 240 has low binding energy. Has low binding energy per nucleon, or I will write EBM. EBM is binding energy per nucleon compared to that of A120. Means I'll write in simple words. Binding energy, see here, I'll write here. Very few nucleus, E binding energy for A is equal to 240 is less than binding energy per nucleon for A is equal to 120. Is that clear? So binding energy per nucleon for A 240 is less than binding. Means if you want to break the nucleons in 240, whose atomic mass is 240, is less when compared to 120. Why it is so? Because of the why it is so? Because of the tightly bound. Okay, nucleons get more tightly bound. Here in this one, nucleons are more tightly bound. More tightly bound. That is the reason. Okay. The second point. Fourth, next point is this gives the concept of nuclear fission. This gives rise to nuclear fission. What is nuclear fission? I'll explain later. Okay. Nuclear fission, breaking of a heavy nucleus into small intermediate nucleus with the emission of enormous amount of energy. That is nuclear fission. The fourth point. Fourth point, it says that when it is A less than lighter nucleus, like two lighter nucleus when it comes together, two lighter nucleus, like how much A is equal to what? A is less than or equal to 10. In that case, if they come together, joining to form a heavy nucleus, joining to form heavier nucleus. Okay, if you want to form a heavier nucleus, bring it together, then it gives rise to so the binding energy will be more. Okay, so binding energy implies binding energy per nucleon is more. So this gives rise to the concept, that is new concept, that is nuclear fusion. Nuclear fusion means bringing combining small nucleus to form a bigger nucleus is said to be the nuclear fusion. That I'll explain later on. Once again, what are the four conclusions? The force is attractive, number one. How? And sufficiently strong to produce a binding energy of pure a million electron volts. The constancy between binding energy here from 30 to 170. The nuclear force is short range, means limited to very small range. A very small, nucleus, that means what? A very heavy nucleus. A very heavy nucleus. That is A240 is less than, binding energy required is less than 120. Nucleons are more tightly bound. Nuclear fission means two lighter nucleus joining to form heavier nucleus. The binding energy is more. Okay, that is nuclear fusion. Next comes nuclear forces. Okay. So there are 3 points here to be discussed here. Nuclear forces. Is this clear, all of you?
Yes, sir.
Yes.
So we have, like, between proton, neutron, there are like these are inside the nucleus. They are friendly. So then when the scientists thought about it, they came to 3 conclusions. Number one, short range. Short range means 10 to the power of -15. It can be, there is -16 also. We have short range, we have long range. But here it is short range. This is in your physics, grade 11, first chapter, physical world. There is a tabular column. Physics, first book, first chapter of grade 11. Physical world, in that there is a tabular column. Gravitational forces, electrical forces, like that. There are 4. So in that nuclear forces, we have short range and long range. This comes under short range. And attractive is very less, very attractive and strong. Okay. So this, please remember this for MCQs. Now I'm going to the next one. That is that is radioactivity. Okay, we'll quickly discuss the discovery of how the radioactivity was discovered. Then can you check, Sriram, whether we have half-life, average half-life, and law of radioactivity decay, this derivation? There are 2 derivations of whether they are
In the
there.
portions only nuclear fission, nuclear fusion is given, sir.
Nuclear fission is then. What about law of radioactive decay?
That is not given in the portion, sir.
Radioactivity?
No, sir.
That is also not given.
Yes, sir.
Alpha decay, beta decay, and gamma decay.
No, sir. Only nuclear fission fusion. After that, they didn't give anything.
No. Before that, what is given? Before beta decay.
Before that, we alpha particles. No, sorry. Composition and size of nucleus. Nuclear force, mass energy relation, mass defect, binding energy per nucleon, and its variation with mass number. Then we finish, no? Nuclear finish, nuclear fusion.
Okay, just I will take 2 minutes to just explain what is the radioactivity, because anyways we came to this lesson. Otherwise, our discussion remains incomplete. Okay, radioactivity. Henry Becquerel in 1896. Okay, Henry Becquerel. Henry Becquerel, he's a scientist. Okay, 1896. This man, he was doing some research on fluorescence phenomena. Photoelectric effect already. Photoelectric effect means when light incidents on a metallic surface, electron ejects at the same time. That is said to be photoelectric effect. Now, that's photoelectric. But fluorescence phenomena is like it will take some time. It's not an instantaneous process. It takes some time. So when light incidents on a metallic surface, it will take some time to come out the electron. So what happened is Henry Becquerel, he was doing this fluorescence phenomena experiment on some few salts. So what happened is it was raining, so he could not expose the salt to the sunlight. He kept all those salts in a drawer of a table, and that there was a new packet of photographic plate. And in those times we did not have any sensors and all to do this experiment. So we have photographic plates, like X-ray plates. You might have seen X-ray films or old photographic plates. You might have seen this. So it was like a sealed packet of photographic plates. That also was there in the same drawer. After like it was raining for 2-3 days, so he did not use that. After 3 days, when the sun came, the sunlight, so he want to expose this salts to the sunlight, and he want to capture the pattern with a photographic plate. When he opened that photographic plate, all the photographic plates were exposed. It was not only one, but in the same pattern it was exposed. Then he started thinking what exactly happened. Then he inquired with the agency also. Then they said, no, it is a sealed packet, no one can use it. Then he started understanding what exactly happened. Then he came to conclusion that there were some salts which were giving out some radiation spontaneously by its own, naturally. So he gave the concept that is where the natural radioactivity came into. Natural radioactivity was discovered. Okay, for which natural radioactivity was discovered. Okay, so now after that, Madame Curie, Madame Curie, Marie Curie, Madame Curie, and her husband Pierre Curie. These two people, they belong to Poland. Okay, so they started doing research on radioactivity. In those times, there was no much only big rich people only can, or like big private organizations used to do the research. Okay, that's up to you. You spend your money and do the research, and you sell your patent or whatever it is. It was like that. Government was not supporting in this thing. So in those days, Madame Curie and Pierre Curie, they started their research work in a car shed, and they found out a new element on radioactivity, and they found out a new element and named after their country, polonium. Polonium was found out by Madame Curie and Pierre Curie, and they named it as polonium because of their country name, Poland. After then, they got the Nobel Prize together. Madame Curie and Pierre Curie, they got a Nobel Prize together in physics. After that, Pierre Curie died in an accident. He did not leave after that, she